Hello friends, welcome to today's lab session. So today we will cover your experiment number 4, which is write a verilog code for SR, DK and JK flip-flop and also verify those flip-flops. Okay. So these are the 3 flip-flops which we'll be trying to cover in today's lab session. So I'll be dividing this experiment 4 into 3 parts, small parts. That is first, in the first part of the video, that is in the first video, I will just explain you the SR flip-flop. In the second, I will explain you the D flip-flop. And in the third, I will explain you the JK flip-flop. The reason behind this is just because, say some students just wants to see the JK flip-flop. Then they can directly view the JK flip-flop video. Okay. So let us start. First, we'll start with our SR flip-flop. So all of you know the SR flip-flop symbol looks something like this. You can see here. So it has you can see 3 input pins. The first pin is set pin, which we say it as yes. The second pin is R pin, which we say it as a reset pin. Okay. And finally, the very important input pin, which is nothing but your clock. So based on this clock, as all of you know, the whole flip-flop will be operating. So SR stands for nothing but set and reset flip-flop. And thereby you have 2 outputs. One is Q, which is a normal output, and another one is Q bar or Q dash we say sometimes, which is the inverted output, which would be inversion of your output Q. Okay. So this is just the basics of your regarding your SR flip-flop symbol. Okay. So since we are writing our code using your behavioral description, the very important thing we need to understand here is your truth table. So therefore, the next very important thing is we try to check upon your truth table. This is how your truth table will look. You can just observe here. The first combination is 0, 0. So when it is 0, 0, you can see that it is previous state and there will be no change in the output. It will just follow the previous output, whatever was there. And when it is 0, 1, the flip-flop is reset. Thereby you can say Q is 0 and the state is reset. And I hope you can easily remember or easily imagine or easily understand the value of Q bar. Q bar is nothing but it is the inversion of your Q. From 1, and therefore we say that the flip-flop is set. And this is one of the major disadvantage or drawback of your SR flip-flop, wherein you can observe that for one of the combinations, it becomes a forbidden state. We don't know what actually is the output. That's why you can see a question mark here in the truth table. Okay. So this is all regarding the theory behind your SR flip-flop. No doubt you have the symbols, you have the logic diagram and all those things, but all those things are not so necessary for your writing of the code. Okay. The verilog code which we will be writing using your behavioral description. Fine. So this is how your behavioral description of verilog code will look of your SR flip-flop. Just 1 second, I will just zoom it up. Fine. So we'll start from the beginning, the first line. So I hope so it's visible. Yeah. So if you can observe the first line here, it is again the time scale. As you already know, it is very important when we do the simulation. So now right now we have taken the time scale as 1 nanosecond. You can, as you already know, it could be changed either to microseconds by just typing here instead of N a U. Okay. Next very important thing is these all are comments, just neglect them. Coming to the main module here. So module followed by the name of the module which we have given SRFF. Okay. Then inside this bracket we will be mentioning all your inputs and outputs. You can observe SR is my 1 input and clock is my second input. Q is my output and Q bar is my second output. Why SR we have taken merged? Because we will be giving a case statement. As you already know, case statement will be working only on one variable. That's why we have taken SR and we have taken them as 1 down to 0. 1 down to 0 means what now? SR0 and SR1. So in that case, if you go back to your truth table, this would be the first input would be your SR0. The second input would be your SR1. Instead of S separately and R separately, we have taken them in the form of an array. The reason behind this is so that we can apply the case statement. That is the simple reason. Okay. Followed by that, you have another input clock and two outputs, Q and Q bar. As you already know, whatever outputs are there, they have to be again mentioned in the form of a register if you are writing the code in the behavioral description. So we have taken Q, we have assigned the initial values of Q as 1 and Q bar also as 1. So this is necessary so that no garbage value is being taken by your. Next, we need to create a sensitivity list. You can see the whole flip-flop is depending on the sensitivity of your clock. So therefore, we are written always at pose edge of clock. That is positive edge of clock. Whenever there is a positive edge of the clock, whenever there is the rising edge of the clock, at that time, the always will be activated. Okay. So once this is activated, next comes is your case statement. It will come inside the case statement. Here it is checking two values. That is SR0 and SR1. Okay. So you can just see the first combination here, SR0 as well as SR1, both are 0, 0. So when both are 0, 0, the output is nothing but what now? It is previous state. So that's why we have assigned Q is equal to Q. Okay. So you can just observe here when it is both are 0, 0, what it is? It is previous state. That's why you are written here what now? It is Q is equal to Q. Next comes is your 0, 1. So when it is 0, 1, we have taken that the output Q is equal to 0 as per your. Okay, you can observe here it is reset state, the second one. Next comes is your set state. So for 1, 0, it is set. Finally, for 1, 1, we have taken forbidden state as high impedance. You can either take it as high impedance or you can take it as unknown state. Anything is okay. End the case, then Q bar is nothing but it is not of Q. Whatever Q the values are taking here, it will just negate it and it will give you the output. So end your begin, that is end your always, finally end the module. So I hope the code is pretty simple. So for this code, we will be writing a test bench now. So we have a tradition, as you already know, that we name the test bench with the name of stimulus. So module, stimulus. Again, whatever my inputs are there, they have to be mentioned in the form of a register. So you can see here both the SRs, that is SR0 and SR1, as well as clock are mentioned as registers. Next comes is your wire. So you have two outputs, Q and Q bar, which are mentioned as wire. Fine. Very important step, this one, we need to link our main module to this test bench. How do you link it? By giving the same name of the module which has been given for the main module, that is for the code module. So for the code module, what name you have given here? SRFF. So the same name must come here, which is nothing but SRFF. Okay. Then only this test bench will be getting linked to the your logic, that is SR flip-flop logic code. Okay. Next, the instance name, any name you can give here, no compulsion that what you can give your own name as well, as I keep on telling. Followed by that, all your inputs and outputs inside the bracket. So you need to initialize your clock. So initially you have taken clock is equal to 0. This is very important. Most of you make a mistake here. You don't write a less than sign here. So if you don't write a less than sign here, it will never negate. So if I want my clock to be negated, say for example, the first pulse is high, the next pulse should be 0. If I want that to happen, then without fail, you need to write this less than sign. Then only the clock will be negating. So make sure that this is one of the mistakes which we see most of the times which students make. Next, we go on initializing our inputs now. You can see here we have written the whole truth table starting from 0, 0, 0, 1, 1, 0 and 1. With a delay of 50 nanoseconds. You can vary this delay as per your interest. Okay. Finally, the display thing. So you know that if I want to display anything, I'll be using $monitor. Then we know that SR is equal to percentage B. You know the meaning of B. B is nothing but what now? It is binary. That means the values which we have written here will be taken in the form of binary. Remember, this has to be written in the same sequential order how you have written here. SR, then here I should write first SR itself, so that the values get mapped correspondingly. Okay. Finally, end the module, and this is nothing but end of your work test bench. Okay. So this is done. The next very important thing after doing this is you need to do the check syntax. So you would find something like this. You need to expand this synthesize and then do check syntax. Remember this thing. Okay. Then we'll be going for simulation. Remember again, very important thing here, most of the students are making a mistake that you should always execute the top module, that is stimulus, not the second module, SR11. You should always execute the stimulus module. Remember this thing. Okay. So do the behavioral check syntax, the first step, inside simulation. Next, you will be doing simulate behavioral model. Okay. So thereby, you will be getting the outputs. So if I want to see all the outputs, just click on this fit to screen button. So I have clicked on this fit to screen button. Let's go and check your outputs. So the clock is high here. The clock is high. You can see your clock is high. S and R both are 0, 0. So it is just following the previous state, which is 0, 1. Whatever the previous state will be there, that will be followed. Okay. Next comes is your 0, 1. Again here clock is high. Please see the output when the clock is high. Sometimes you will see the output where the clock is low. No doubt you will get the correct output, but when you show for the examiners, try to show when the clock is high. So the clock is high here. S and R, S is 0, R is 1. So therefore you can see it is reset. That is Q is 0 and Q bar is 1. Then when it is 1, 0, you can see Q is 1. That is the flip-flop has been set and Q bar is 0. Finally, when it is 1, 1, you can see that as per our notations, we have given it should be high impedance Z. So therefore you can see a Z in your waves. That is forbidden state. So friends, regarding your SR flip-flop, that is the first part of your experiment number 4. So I'll stop this video here only. In the next video, I will cover your D flip-flop so that it will be easy for you to follow. Okay. So if you have any doubts and problems, you can just meet me or buzz me. Thank you for watching.